I'm Amanda Liberty, the coordinator for the Rangeley Lakes Heritage Trust. At the Rangeley Lakes Heritage Trust, we do conserve land, water, and public access within the Rangeley Lakes region. Tonight's program is the second in a series of dark sky events that we've got planned for you in 2023. And we hope that you will join us on March 16th for another dark sky tour, hopefully in person. And also please stay tuned for our events that we'll have coming up on the week of April 16th, which is International Dark Sky Week. This evening's program is sponsored by Dark Skies Rangeley, which is a community-led effort to conserve the dark skies over Rangeley Lakes. And with that, I'll hand it over to John Meter of Northern Stars Planetarium.
Thank you, Amanda. Hey, everybody. I know some of you have probably been on these before with me, and I'd like to welcome you all. I was really hoping I was going to be in Rangeley tonight, do a nice snowshoe tour and look at the real sky. But you know, the weather doesn't always cooperate the way we want it to. So we're virtual tonight, and I'd like to jump right in and take a look at that virtual sky. And oh, Amanda, I need to have you give me sharing privileges. I hope you're still there. Oh, there we go. Thank you. Let's go to here. Here we go. And we'll go to bring up all thing here. So hopefully you can see the screen in front of me now. And there we go. And we're looking, this is at a little bit early. This is at 6:30 tonight. So this is a half hour ago, or an hour and a half ago. And since it's cloudy tonight, I wanted to start a little earlier because if you get outside tomorrow night or some night this week, if we get a clear night, hopefully you will. And you get out around 6 or 6:30 and look in the western sky, and you're going to see two incredibly bright stars over there. And those two bright stars, which you see right here, turn out to be planets. The one on top is the planet Jupiter, and the slightly brighter one underneath it is Venus. Now, in our solar system, if you know anything about it, you know that Venus and Jupiter aren't anywhere close together. They're actually quite far apart. Venus is between us and the sun, and Saturn and Jupiter's away from the sun from us. So they're kind of in opposite directions, it seems. Yet the way they're lined up in the sky, since the planets go all the way around the sun, sometimes they'll look like they're next to each other when they really aren't. They're still millions of miles apart, but they're going to get closer and closer. So here are our two planets, Venus and Jupiter. Now, if we had a telescope, Venus isn't an awfully exciting planet to look at, but Jupiter can be really cool to look at. So let's begin by just taking a look at Jupiter as if we were outside and set up a telescope and looked at this planet. Now, what can you hope to find? Well, you can see the planet itself. And what you're seeing here, you can see some red bands. If you look through a telescope, you're going to see those two distinct bands, this one and this one right here. I'm going to get rid of those blinking things. Those are cloud bands. Jupiter is a gas giant planet. This planet is big enough you could put 1,000 Earths inside of it. So it's really, really big, bigger than all the other planets combined in the solar system. But there's no ground. We're not going to land rovers and drive around on Jupiter like we did on Mars because there's no ground to drive on. It's all clouds and gases, and the wind blows through these clouds. In this white band in the middle, it blows westerly at like 100 miles an hour, while the two brown bands on each side go easterly at about 100 miles an hour. And that occasionally creates storms like the Great Red Spot. We did this last night up at the AMC, the Appalachian Mountain Club's lodges, and the red spot was dead center. And you see tonight it's not. So it's around on the other side. But so you can see those bands, but you're going to see it all kind of in grayscale. You won't see color. Color comes through and you take a photograph of it. The part of our eyes that sees faint light, the rods, remember cones and rods when you were in school? Cones let you see color. We love color, but they need a lot of light to work. And the rods can see very faint light, but they pretty much see in black and white. So when you look at things in space, lots of things which you take pictures of show bright color. To our eyes look black and white. The other thing you see are the 4 largest moons. Now, you may have heard recently that we've discovered Jupiter has more moons than we thought. And we thought it had quite a few, like 79. We now know it's up to 96 moons going around this planet. Imagine 96 moons in the sky, because they're not all as big as our moon. There are 4 big ones. You can see them here, 1, 2, 3, and 4. And they orbit back and forth. So we got 2 on each side tonight. If you go out tomorrow night, you might have 3 on one side and 1 on the other. Sometimes all 4 are on one side. They're orbiting, they orbit at different speeds. The one closest, Io, goes around quickest, while the ones further out, like Callisto and Ganymede, take a little longer to go around. And sometimes you can't see all 4. Sometimes you only see 3 because one might be behind the planet. And occasionally it can be right in front of the planet, and that can be problematic to see too. But it's always fun to look at Jupiter and see how many moons you can see. And they look bigger here than they'll look. When you look through a telescope, they're going to look like pinpoints. This is just a function of this program so that they show up well. So that's Jupiter. Now, the other interesting thing about Jupiter and Venus is that Venus, being close to the sun, moves quicker than Jupiter, and it's moving towards Jupiter. So what I'd like to do is just jump ahead here. Let me just put a lock here so we can stay right on Jupiter. And let's just jump ahead by the day here for just a moment. So this is today, the 20th of February. Watch what it does as we go night to night. See how it's moving closer, and look at the moon, which will be coming up here. This is just 2 days from now. It's going to be right almost on top of Jupiter. It's going to be very, very close. That'd be an interesting photograph, wouldn't it? I have to remember that if it's clear and I get a chance to go out. I want to pass the moon because on the 1st of March, these 2 planets are going to be less than half a degree apart. They're going to be really, really close. If you look, they look like they're touching each other, but they're not. If we go in, you can see that they're actually pretty far. There's a gap between them. It's not like one's going in front of the other, but they're going to look very, very close together. That's called a conjunction. And that's March 1st. We go back to the 28th or a little further. I think March 1st is the day they're actually closest, and that's next Wednesday, I believe, Wednesday or Thursday. So that's how it's going to move. You notice Jupiter's not moving very much. Being far from the sun, it takes a lot longer to go around the sun, so it moves slower across the sky while Saturn keeps climbing. Well, I want to jump back to today, so let's just jump back to right now. Let's back up here. And if we go to right now, which is a little after 8, you're going to find that Jupiter's dropped down. Remember I said we went at 6:30 earlier. Now we're right to the moment of what it looks like now. Venus is below the horizon, and Jupiter, you can see, is just barely above the horizon. So they set pretty early. And if you want to see those two, you got to get out a little earlier than 8 o'clock. Well, let's swing around to the southern sky. Let's back up so we can see a little more sky here. And I want to talk a little bit about my favorite part of the summer, the winter sky. This southern region is just such a rich region. There's some beautiful constellations here, some fascinating stars, and you can actually go through the whole life cycle of a star just by scanning around here with binoculars and a small telescope. And it all starts with the constellation that you might know called Orion the Hunter. Orion, everyone knows Orion's belt, these 3 stars in a row. And if that's all you know of Orion, you've missed a whole lot because there's more to the guy than a belt. The whole man's here. We've got a leg coming down to Rigel and a leg coming down to Safe. And you might notice his belt looks like it's tugged down towards Safe. And that's because there's a sword hanging from his belt, and it's heavy and it tugs his belt down. Above his belt, he has a body up to Beetlejuice and Bellatrix. Yeah, and they were named that before the Harry Potter movies and before that silly movie back in the 90s. They've been named that for a very long time. So those popular culture items, they pulled those names from the stars. So the Beetlejuice and Bellatrix are the 2 shoulders. This little clump of stars marks the guy's head. He's got an arm raised up here with a faint club. You can just kind of make it out of the stars any way you want. Then come back down his arm and across his shoulder. He has another arm coming down, and I use that star as an elbow, and he's holding a shield in his hand. Sometimes it's drawn as the skin of a lion, depending which stories you talk to. I can put some lines up there if you like, just to see it a little bit better. There it is right there. Wait, I'm just going to clear something. Hold on. Let's do it again. We got to pick a different star, though. There we go. Now, you'll find that's a little differently, drawn a little differently than the way I drew it. And if you have 2 or 3 different apps, on your laptop or your phone, there's dozens of apps out there to learn constellations. You'll find they always use the same stars, but they'll connect the dots differently. If you look up in books, remember those things called books, and you find a couple of books on constellations, you'll find they do the same thing. They use the same basic stars, but they connect the dots in different ways. There's not a right or wrong way to do it. As a matter of fact, the only right thing about it is the International Astronomical Union, who divided the sky into 88 constellations. They don't draw the constellations like this. They draw them like this. Everything inside this polygon is Orion the Hunter. And as far as they're concerned, you can connect the dots any way you want. You just need to stay within this polygon. So that's kind of a boring way to look at a constellation in my book. I like this way. Now, when I was a kid, I remember wanting to learn constellations, and I had this beautiful book from the National Geographic. And I took it outside to look at the stars to see if I could learn the constellations. But they didn't have dot-to-dot drawings like this. They had beautiful drawings like this. And they are beautiful, but it's hard to look up in the night sky and see that floating in there and try to make that out of the stars. I never could do it, and I got really frustrated. And I put it away for several years till I got older and was exposed to dot-to-dot lines. And that made a lot more sense. I could see that in the sky. Now, in Orion, because I want to go through this life or death of a star thing here tonight, because I think it's interesting. If you look at Orion's sword, you can see that one of the stars down there looks a little fuzzy, like someone tried to erase it with a bad eraser. Well, there's a good reason for that, because it's not a star. If we zoom in on that, we'll see what we're looking at. Let's just zoom right in here. You'll find something known as the Great Nebula of Orion. And this is a giant cloud of hydrogen gas floating in space. Now, we have clouds of water floating above the Earth. We call them clouds. Well, this is a cloud in space, and it's not made of water. It's made of hydrogen, which is what stars are made of. And this cloud is really big. It's, depending on where you measure, it's from between 20 and 40 light years across. Now, remember, a light year is not a length of time, even though it sounds like one. It's a distance. Like an inch is a little distance and a mile is a bigger distance. A light year is a huge distance. It's the distance a beam of light will travel in a year's time. And light travels at 186,000 miles per second. At that speed, you could go all the way around the Earth 7.5 times in 1 second. That's pretty fast. So if you go at that speed in a straight line for 1 year without stopping, you're going to cover some miles. That distance is 1 light year. Well, from one side of this nebula to the other is, depending on where you measure it, because it's a regular shape, between 20 and 40 light years across. It's huge, but it's shrinking. It's collapsing in on itself, and it's forming new stars. It starts clumping, and once the clump forms, it has more gravity, so it pulls more gas in, and eventually there's enough gas there that the pressure in the center of that clump becomes great enough to start fusion reactions. That's what happens in the cores of stars, and then a star is born. So eventually, if you could come back in 100 million years, and I know that sounds like a long time, but in the life of an average star like our sun, that's like going from being a baby to like a teenager. In 100 million years, this nebula wouldn't be here. In its place will be maybe 200 or 300 stars like our sun. Well, that sounds like a good theory, doesn't it? The question is, how do you prove it? We don't live for 100 million years. Well, if it is true, we should be able to find places where it's already happened. Let me show you a couple. Now, look at Orion again, and you see how if you draw a line down through his belt, it points you to a really bright star. That star's name is Sirius, and Sirius happens to be the brightest star in the entire night sky. And it marks part of Canis Major, which means the big dog. To see the dog, I draw it a little differently. I draw Sirius as his nose. And I have this is an ear, and this is an ear. So that's a triangle where he's staring right at us. This little oval down in here would be his body with a leg there and a leg there. Come down his belly, there's a back leg here and a back leg there and a little faint tail sticking up. I tell the kids his tail's faint because he's wagging it because he's a happy dog. They draw him a little differently here. They use Sirius as his collar and make a different triangle for the head. I find a couple of these stars like this one, I just have a hard time seeing it that way myself. But you can draw the constellations as you want, because remember, really, it's whatever's inside that square, and you can draw it, connect the dots any way you want. So I do them a little differently, but it's still, whether you see it the way I see it, the way they do it here, you can still kind of see a dot-to-dot dog here. What I want you to look at in our quest to understand the life cycle of a star, they're all born in these nebulas. Then they form into what are called open clusters. And if you find Sirius, which is pretty easy to find, draw a line down to Sirius and look underneath it with a pair of binoculars. And if you're in a dark spot, you can just barely see this with your eyes. It's right in there. There's a little fuzzy patch. So we're going to zoom in on that like we had a pair of binoculars. And you're going to see a little clump of stars all together right here. This is called Aristotle's cluster, or M41. And it's named because Aristotle wrote about it. He could see it. It was darker back then. They didn't have the light pollution we have today. And so they could see this little cluster of stars. These are young stars. These are like teenage stars. They're maybe 100 million years old. And for a star, that's being pretty young for the most part. So if you could have looked in this spot 100 million years ago, these stars wouldn't have been here. What would have been in their place? A nebula, just like the one we saw in Orion. If you want an even better example, go back to Orion again and go up through his belt, and it's going to point you to two clusters. The first one is the closest cluster to us, this little group of stars here called the Hyades. That's the closest open cluster to the Earth. It's about 153 light years away. And these are all fairly young stars. The bright star Aldebaran is the brightest in the group, but it's actually not part of the cluster. It's only 65 light years away. It just happens to be between us and the cluster. They're kind of lined up the way Venus and Jupiter are lined up. They're not close either. They just look close. The same with this. But the most famous open cluster is just beyond the Hyades. It's called the Pleiades, and it's right over here. To see the Pleiades, you can see it with your eyes. They're known as the Seven Sisters. And if you look at them through, with just your eyes, you can tell that there's 4 or 5 or 6 stars there. Most people have a hard time seeing 7. The interesting thing is all over the world, people refer to this group of stars by the number 7. And all over the world, people told stories about why you couldn't usually see 7. I find that interesting. The Japanese had stories like that. The Greeks had stories like that. Native Americans had stories like that. Well, if you've got your binoculars and you check them out, let's zoom in and see what you see. You see way more than 7 sisters, right? There are actually about 150 stars or so here. This is an open cluster. This one's about, I think it's 70 to 100 million years old. And it's beautiful. Now, when here it looks like little white dots, like someone had a hole punch and they punched a whole bunch of holes on a black piece of velvet or something. It's even prettier when you look at it live with the telescope, or even better with binoculars. This is one of the few objects that's better in binoculars than in a telescope. Telescopes look at a small part of the sky, and when you look at the Pleiades with most telescopes, you can't see the whole thing. You just see a little part, like this part or this part, because telescopes look at a small part of the sky, whereas binoculars can see the whole view in one viewing. Now, so it's really pretty. It looks like a pile of diamonds. They really do sparkle. If you take a photograph, then it looks like this. It's even prettier because you can see some of the nebulosity around them. You won't see that with your eyes. It's too faint and the surface light is too dim. But with photography, which can gather light over time, those faint features start coming out. And then you can start to see some of that nebulosity, and it's really, really pretty. So those are the teenage stars. So you think about teenagers, they like to hang out with their friends, and so do teenage stars, it turns out. Now, they won't stay together forever. Slowly over time, they're going to drift apart. And there's not enough gravity to keep them together as a group. They'll drift off. And I always tell kids that, teenagers hang out together, then they graduate high school, and some go to this college and some go to that college, and some get jobs, and some join in Army or the Navy and NASA or whatever, and some get married. Well, stars don't join NASA and they don't go to college, but they do get married. If 2 stars happen to be close together, they will go into orbit around each other, and they just got married. That's called a binary star system. The difference between people and stars is that you got 2 stars happily married going around each other, and the third one comes by, it'll join in. And the fourth one comes by, it'll join in. For example, Sirius is a binary star, 2 stars, a big one with a little one going around it. If the stars are different sizes, the little one goes around the big one. If they're the same size, they go around each other like 2 people actually dancing. Rigel over here is actually 4 stars. So imagine you've got 2 stars orbiting each other, And then there's a bigger star, and those two stars go around the big star. So you got two little ones going around each other. Then those two little ones together go around the bigger one. And then there's an even bigger star, the major Rigel A, and that system of three goes around the big one. Now that's a complicated relationship right there. So here we have found a teenage star, and here we find a more mature star. And up on the other side, you might notice that Orion has a reddish orange star in his shoulder, Betelgeuse. That's a fascinating star. This star is really young. It's only 10 million years old. That's a young star, right? Our sun is 4.5 billion years old, way older. I find a lot of kids, I teach kids a lot, and I find that kids don't understand the difference between a million and a billion, that they're really different. So I just recently learned a way to really describe it in a way that seems to make sense to a lot of people. So think about this to understand the difference between what a million and a billion is. Think about a million seconds. A million seconds is 11.5 days. I think we can all imagine the length of time of 11.5 days. Even elementary kids can do that pretty easily. A billion seconds is 31.5 years. A billion's a way bigger number than a million. And if you want to take it another step to a trillion is 31,600 years. So these numbers get big really fast. So our sun is 4.5 billion years old. Betelgeuse is 10 million years old. It's a baby compared to the sun. The difference is it's a much more massive star than our sun. And big stars that have a lot of mass burn their fuel furiously. The idea is they live hard and they die really young. The star is going to die before it's 15 million years old, probably, maybe sooner. It's going to supernova and explode. So big stars like this die young. And when I say it's big, let me give you an example of what I mean by size. Remember, I said Jupiter was 1,000 times bigger than the Earth. The sun is 1,000 times bigger than Jupiter. That's over 1,000,000 times bigger than the Earth. Now imagine the sun is a beach ball 2 feet in diameter. Bring Betelgeuse over and set it down, on the shore at Rangeley Lake. You got this beach ball 2 feet in diameter sitting there. Blow up the beach ball the size of Betelgeuse. It's a beach ball 1/4 mile in diameter. It's huge. And so it's burnt its fuel vigorously and it's going to explode one day. So what would that look like? Well, let's find a place where a star has already done that. Remember we went up to the Hyades? Well, here we have Orion the Hunter. Let's put some lines back up here. Here we have the big dog. The Hyades mark the face of Taurus the bull. Aldebaran, the bright orange star, is one of his eyes. I use this as his other eye. Kids always want 2 eyes. They want to know, where's the other eye? So I tell him he's in a fight with Orion because Orion's got his shield up in his club rays. They're fighting over the 7 sisters riding on his back. And we've got 2 big horns coming up here. This is his back. This is one front leg. One thing I don't like about this program is he has another front leg right here. And it's much better to have 2 legs. And I usually draw a line like this for his belly coming up too. It's just the bust, the front half of the bull. He's charging at Orion. Well, if you go right up his left-hand horn and look just inside right about here, you're going to need a telescope. You won't see this with binoculars. What you're going to find here will be the remains of a star that has just recently died in the last 1,000 years or so. It's right over here. And it's called the Crab Nebula. So here it is right here. Now, this is a nebula like the Orion Nebula. It's a big cloud of gas. The difference is we can tell what stars are made of by looking at that spectrum. You take the light of a star and put it through a prism, you get the rainbow, right? Which scientists call a spectrum. What you find when you do that with a star and you spread that rainbow out, you find black lines going through it, which correspond to different elements. Each element has its own set of lines of wavelengths it absorbs. If you look at the Orion Nebula, it's all you have for absorption lines there are a signature for hydrogen. That's all that's there. You look at the spectrum of this, and you find there's hydrogen, there's helium, there's neon, there's carbon, there's oxygen, there's iron, there's silver and gold. Silver and gold is only created after stars explode for the most part. stars can create elements up to iron. And once they start creating iron, they don't have enough energy to keep things going. And they collapse on themselves, make one giant nuclear explosion that in 1 second can give off more energy than all the rest of the stars in the galaxy combined in 1 second. And when that happens, it creates all the elements heavier than iron. That includes all the gold and all the silver on the planet Earth. So if you have a gold wedding band on, or silver earrings, or any piece of silver and gold jewelry, you have a piece of a supernova. If you're wearing it now, you have a remnant of a supernova on your body at this moment. That's kind of cool. It was created in an explosion like this. This explosion happened 950 years ago in 1054 AD. And we know the exact date is on the 4th of July that year. And the Chinese wrote about it, and they called it the guest star. Now, to them, they didn't have telescopes back then. They were just outside looking at the stars, and suddenly a brand new star appeared in that spot. And that star was so bright, they wrote that you could read by it at night. Now, it still was a pinpoint of light, but it was the way Sirius is brighter than safe. This star is brighter. It was as bright as the full moon, but it was a pinpoint in the sky. And you could see it during the daytime, and at night you could read by it. It lasted for 3 or 4 months, and then it faded away. What you just looked at, the Crab Nebula, that's what's left of it today. That's expanding outwards at 1,000 miles per second in all directions. And that's what it looks like after 950 years. So right here, between these 3 constellations, we found where stars are being born. We found 2 spots, or 3 spots, M41, Aristotle's cluster, the Hyades and the Pleiades are young teenage stars. We found Sirius and Rigel, which are adult stars, so to speak. We found an old dying star here, and then we found a star that's already died up there. I think that's pretty cool. All in one part of the sky. And most of these things you can find with just a pair of binoculars or a small telescope. You can see M41, the Hyades, the Pleiades, and the Orion Nebula easily with a pair of binoculars. The only one you need a telescope to see is the Crab Nebula up here. Now, one more thing, right? You notice this bright star we've kind of ignored here on the other horn of Taurus. That's not a star. That's the planet Mars. And Mars is slowly moving eastward through the sky. It doesn't move as fast as Venus, but it moves faster than Jupiter. So you're going to find over the course of the next couple of months, it's going to move out above Orion and into the Gemini twins right up here, Castor and Pollux. Pollux is on the left and Castor's on the right. And they're just dot to dot stick people standing above Orion. So we have Orion the Hunter, and we have Canis Major, and Taurus the Bull, and the Gemini twins. Now, if you think about Canis Major, that kind of implies there might be a Canis Minor, right? Well, there is. Just go from Sirius, go up towards the Gemini twins, and you notice there's a bright star between the two. That's Procyon, and that's the nose of the little dog, Canis Minor. And Canis Minor is a really simple constellation because it's just 2 stars, Procyon and Gometia, with a line between them. Doesn't look much like a dog. Not every constellation is as good as others. These other ones, the big dog, I think you can kind of make a dot to dot dog, and Orion makes a pretty good guy. The bull, I don't like the way they drew it here, but I can see a bull charging at Orion because I've been doing this for a long time, so maybe I'm just seeing things. And then you can find the Gemini twins, pretty good stick people. This just doesn't look like a dog, but it does kind of look like a hot dog. So that's the kids and I have agreed that that's what we'll call it, is the hot dog instead of the little dog. So there we have some of my favorite constellations of the winter sky. Now that dog, the big dog, looks like he's jumping around like he's all excited about something, and he is. He's leaping after Lepus the hare right down here. The rabbit is jumping away from the dog. Now, I, again, draw it a little differently than they'll draw it on here. So I want to show it to you my way first, because I'm teaching you, so you have to listen to me. This little trapezoid is the rabbit's body, with this pointy end being his head. He's got 2 ears sticking up, one there and one there. Come back to the back of his body. He's leaping away from the dog, so he's got a hind leg stretched out here and a hind leg there. Then we come up to the star, and we don't want the poor little guy to land on his face. We give him a couple of front legs, one there and one there. So there's our rabbit. Now they draw him totally differently. They use the same stars, of course, but they give them a ridiculously long tail. I've never seen a rabbit with a long tail, but there are a couple other animals in the sky that give long tails too that don't have long tails too. I guess they just like tails in ancient times, perhaps. But it goes along well with the dog because you can see the dogs all excited. These two dogs are running in circles, chasing the rabbit while Orion's busy fighting the bull, trying to rescue or save. There's all kinds of stories about what he's trying to do with these 7 girls. And then we have the Gemini twins standing here kind of on the faint band of the winter Milky Way, watching the whole thing take place. Now we're going to look over in the eastern sky, come over in the east, maybe a little bit further all the way to the northeast. You know, we're past the halfway point of winter. Groundhog Day is cross quarter day, which means that's the midpoint of the season. And so we're past that now. We're headed towards spring. And when you go out at 8:30, like if you're out right now, I would look in the east and see this constellation, which is one of my very favorites. It's called Leo the Lion. Let's take those other lines down for now. And to see Leo, what you want to do is look in the east and look for a group of stars that's shaped like a question mark. It's right in here. The only problem is it's backwards. It starts with the star and it curves around and comes down with a bright star Regulus for a dot. It makes a pretty good looking question mark. You're just facing the wrong way. They usually go the other way. Now, this is not the constellation of the backwards question mark. It's the constellation is called Leo the Lion. So the question becomes, how do you turn a backwards question mark into a lion? Well, you do that by adding some stars. So take the curve of the question mark and just continue it around and make a circle out of that. That'll be Leo the lion's head. The curve of stars you see is the furry mane on the back of his head, and his face is over here where there aren't any stars. You have to pretend that part. To make a body, we go from the bright star Algebra back to this star. I think it's Zosma. Then come down to this one, up to Regulus, and then back up. And this is the lion's body right here. He's got a tail down to Denobla. Come back up to Zosma, come down here, and you've got these 2 lines for 2 back legs, one here and one there. Come back up his belly. There's a front leg here and a front leg there. They do not a bad job putting the lines on for the lion. They don't give the legs out, but you can easily imagine a front leg here and a front leg there, and the 2 back legs, one here and one there. And so there's his head and his mane. So there's Leo the lion. If you're wanting to see a fancy picture of him, it helps you visualize them perhaps a little more. I find sometimes these can be really useful once you kind of get a good grasp of the dot-to-dot drawings to visualize it. Then you can come back and use that combination to make this a sense of that constellation. Now, I like Leo because Leo is really a springtime constellation. It's starting to come up now, and that's the sign spring is on its way. By May, it's going to be way up high in the southern sky, not down low in the east. And then it's just right in the prime of spring. Now, if you have that telescope, there's a couple of cool things to check out here. First of all, remember we talked about how some of the stars are binaries or doubles. Well, Algebra, this one right here, that's a really cool double. So you want to take a look at this star and zoom in with your telescope. That your eyes is going to look like one star. But watch what happens when we get in close. It should split. Oh, it's not going to split for me today. Oh, I have it set wrong. You can change the setting of the size of these stars. I make them bigger. You can make them bigger or you make them smaller. And I found on Zoom, if I make them smaller, they look good on my screen, but they just disappear for you guys. And I've made them too big to separate these 2 out. What's kind of cool about those 2 stars is that they really stand out as different colors too. So it's a really pretty binary. I've just made the stars too big so that people on Zoom, like you folks, or on Facebook, if you're watching there, can actually see the stars on this program. So I apologize for that. I should have checked and I didn't. Another cool thing you can see, so that's the double star, 2 stars orbiting each other. Half the stars you look at outside of night are actually more than 1 star. They're just so far away and so relatively close together that they look like 1 star. But with a telescope, you can split many of them into 2. Now, right under his hind leg, right in here is a really cool place to look if you've got a telescope. Let's get centered here so we can zoom in on it. Because what you'll find here is not a double star. you're going to find 3 galaxies right next to each other. It's called the Leo triplet. You can see them right here. And the nice thing is you can get them all in one field of view pretty easily. So this one's called M65 and 66. I may have those backwards. Let's see, will it give it? No, it just says Leo triplet. I think it's M65 and M66. And this one's called the Hamburger Galaxy. What M stands for is Messier. Charles Messier was a French astronomer in the 18th century, and he didn't care at all about galaxies. They didn't know what galaxies were back then. He was a comet hunter. He's hunting for comets. And there are all the, and comets, especially in small telescopes like he had, look like fuzzy stars. Well, these things look like fuzzy stars in small telescopes. The Orion Nebula looks like a fuzzy star. That's why it's M45. And no, M43, excuse me. No, M42, excuse me. I get my M numbers all mixed up, so you have to forgive me on that one. So he cataloged 109 of these things, and they are some of the best things to look at with a small telescope. And he didn't care at all about them. He just was cataloging them so he wouldn't confuse them with comets. So I want you to look at M65 and M66 here first. Look at this one. If we zoom in on it, you can see it's a spiral galaxy, like our own Milky Way. We've got these spiral arms coming out from a dense center in the middle. And you see the darkness are dust clouds and things between the stars. Now look down at this one. This is a spiral too, but you can see it looks a little different. We're at a slightly different angle. But what I want you to notice is all the pink patches there. Those are nebulas like the Orion Nebula we saw. So this galaxy is full of them, and the other one didn't seem to have many. Well, some galaxies have a lot more than others. And the ones like this one that have a lot have usually been in a collision with another galaxy. When 2 galaxies interact, they stir up all the dusts and all the gases, and it gets all that activity going, and it creates new star formation regions. So they believe this galaxy and the Hamburger Galaxy had recently collided, recently in the last couple 100 million years. And when they did, when galaxies collide, there are almost no actual collisions. Stars are too far apart to actually hit one another, but it stirs up the gases and creates all these nebulosities in here. Now, the Hamburger Galaxy, we're looking at, it's a spiral too, but we're looking at right edge on. So spiral galaxies are kind of shaped like Frisbees. They're round like a Frisbee, but flat like a Frisbee. So here you're looking down at like a 60-degree angle. This one's about a 45-degree angle. This one's looking edge on versus a face-on galaxy. So they're all, and it's called the Hamburger because those dust lanes in the middle kind of look like the hamburger between the buns, perhaps, I guess. But it's a nice little area to look with your telescope because you've got 3 galaxies really close together, and it's at a spot that's really easy to find right underneath the hind leg of Leo the lion, right there under Churton. So it's a really neat place to look and explore. Now, right above Leo, if you have a hard time finding Leo, here's the way to do it. Find the Big Dipper. Do you see the Big Dipper? It's right here in the northeast, standing up by the handle. 3 stars for a curved handle, 4 stars for the pot or the bowl. Now, technically, the Big Dipper is part of Ursa Major, the Great Bear. We add a few stars to the Big Dipper to turn it into a bear. And here's another one with a long tail. And just like rabbits, bears don't have long tails, but the one in the sky does, and there are lots of stories to explain that. The handle becomes the bear's tail. The dipper plus these 2 stars make up the bear's long, skinny body. Excuse me. Now, when I draw this, I don't draw this line at all. I draw a line between these 2 stars for a body. Then I have these lines coming down for the front legs, this line coming down for the back legs. Sometimes you'll often see another line coming down to these 2 stars. So this would be one foot, and this would be the other foot, then the 2 front legs together. And the pointiness here obviously goes to his nose with his face up here. Pretty weird looking bear, huh? Put some lines up there. You can see the bear with a long tail right above Leo the lion. And there are lots of great stories explaining why this bear has a long tail. And we're not going to get into that because that's a whole nother venue. But here is this one hopefully will divide out. So look at that middle star in the Big Dipper's handle. Shut the lines off. Get rid of my little circle. Just look at it. How many stars can you see there? Let's go a little closer. And you should quickly start to see 2. The brighter one is Mizar. The fainter one is Alcor. And if you have a telescope and you zoom in closer, you'll see there's a third one in between the two. That's Ludwig star. And it's named after a German prince from the 18th century. When it was first seen, they thought it might be a planet going around one of these stars. We now know it's just a distant star, much further away than the other two. These are actually now, for a long time, there's a debate whether they're gravitationally held. They are almost exactly the same distance away, about 85 light years, I believe, whereas Ludwig star is 160 light years, twice as far away. So these are generally, in most of the literature I've read recently, believed to be gravitationally bound together. So they are probably orbiting each other in a very large orbit that takes thousands of years. But if you get out your telescope and increase your magnification a little bit, look at Mizar, the brighter one, and look what it does. Hey, that one did split for me, didn't it? That's Mizar A and Mizar B. So what started off at a glance looking like one star quickly turns into two. And then if you add Ludwig star, it's three. And then Mizar turns into two. So that turns it into four. And scientists study them with, remember we talked about spectroscopy and taking the spectrum of a star. If you take the spectrum of Mizar A, it has two spectrums, which means technically it's actually two stars. They're just so close together we can't separate them optically, but there's two there. And this one has two spectrums, which means it's two stars. So Mizar is actually four stars. And if we do the same thing with Alcor, it's two spectroscopic stars. So what started off at a glance looking like a single star in the handle of the Big Dipper actually turns out to be 7 stars. Another complicated relationship. So let's bring up our lines again here. We have Ursa Major, the Big Bear, Leo, the Lion. And once you find the Big Dipper, which is part of the Great Bear, most people want to find the Little Dipper next. To find that, you go to the back 2 stars of the Dipper's pot. They're called the pointer stars. Their names are Merrick and Doobie. So you draw a line from Merrick to Doobie, and you doobie right across the sky, and it'll point you up to this star. That's the North Star, Polaris, probably the most famous star in the night sky. It's not nearly the brightest. The brightest star is Sirius, that nose of the big dog or the collar, depending on how you draw it. But this one's famous not for being bright. It's about the 48th or 49th brightest star, depending on how you split doubles, whether you count them as 1 or 2. So it's not famous for brightness. It's famous because it's directly above Earth's North Pole. If you were standing at the North Pole, you'd look right straight up to see it. Well, we're not at the North Pole in Maine. In Rangeley, you're at about 45 degrees. I've seen that little sign in downtown that tells you you're halfway between the North Pole and the equator. So that means if you measure the height of the North Star above the north horizon, the closest straight line from there to the horizon, and you measure the angle, if you're standing in Rangeley, it'll be 45 degrees up in the sky, within a half a degree. Now, if you were in Portland, where it's 43 something degrees, that would be 43 something degrees in the sky. The height of the North Star above the north horizon is always equal to your latitude. Think about it. If it's straight up at the North Pole, your latitude is 90. Angle to straight up is 90 degrees. If you go to the equator, your latitude is 0. You know where the North Star is at the equator? It's right on the horizon. So you can use it to tell the direction. It's always in the north. And you can also use it to determine your latitude within a half a degree. It's also part of the Little Dipper. And the Little Dipper is the same thing as Ursa Minor, the Little Bear. We don't add any stars to make a Little Bear. It's just the square, which is the pot of the Little Dipper and the handle. And again, it becomes the bear's body with a long tail. Now, not everyone saw it as a bear. The Greeks made it into a bear, but many of the native stories call him Little Fisher. This one's always a bear, but many natives refer to this as a fisher. So not everyone sees everything exactly the same way. Go back behind the Dippers, and over here in the northwest, you're going to find a zigzag in the stars, and that's Cassiopeia, the queen. And it looks like a letter W or an M, depending on which angle you look at it at. It doesn't look much like a queen, though. It's usually drawn as a lady sitting in a chair, something like this, a queen in her throne. And she was known for her vanity, so she's often shown looking at herself in a mirror. I have a hard time looking at a W and seeing a lady sitting in a chair. So the kids and I've seen hundreds of thousands of kids in my 40 years of teaching in the planetarium. And we've all come to the agreement that it should not try to be a lady in a chair. It's simply her crown, a three-pointed crown. And there's the bottom where the Queen Cassiopeia would put her head. Now, queens have daughters called princesses. And right beneath her, over in the western sky, you can see Andromeda, the princess. This is her head. This is her body, this triangle right here, like this. This is the belt going around her waist, those three stars. She's got a leg coming up here and a leg coming up there. And you can just barely see the hem of her dress right there. Very delicate. Now come back up to her triangle-shaped body, and we have an arm with those three stars and another arm with those three little stars. Not a bad dot-to-dot person. She's floating upside down, but you can do that in space, right? There's no up or down in space, so you can float any way you want. They don't draw her that way. I absolutely hate the way they draw this because I think it makes a pretty good dot-to-dot person. They just draw it like this, one side of her body and her belt. But that's useful in one way because right above her belt, right at the Cassiopeia side of her body, you'll notice it looks like there's a fuzzy star there too. Well, that is another galaxy. This one is the Andromeda galaxy. And this one you can see without a telescope. With just your eyes, if you're in a dark spot like you have in the Rangeley area, if you get a clear night, look in the western sky, see if you can find Cassiopeia, then see if you can find the upside down, that V shape, which is the upside down princess. And right at halfway up the right-hand side, you'll see that little faint patch of light. It'll kind of look like a very faint star that someone tried to erase with a bad eraser again. That's the best way I can explain that to you. And when you look at that, you're looking at, that's the most distant thing you can see without a telescope. This galaxy is 2,500,000 light years away. So the light that's entering your eye when you get out there some night this week and you see that little object, you should realize the light that's entering your eye left that galaxy 2,500,000 years ago, only to enter your eye at that moment. That's kind of cool. Now, if you have a pair of binoculars, you might want to zoom in. And with binoculars, it's going to look like a fuzzy patch of light, just like this. I think that's a great illustration of what you can expect to see in binoculars. Yeah, and you'll get a sense that it's kind of oval shaped. If you back off just a little bit, you get this oval shapeness about it. It's all stars. Now, if you have a decent telescope, you get more definition. A big enough telescope, you can actually see stars within it. And if you want to see it really well, photography does a good job. It'll look like this. And it's very, very beautiful. And so this is the Andromeda galaxy, and it has two little galaxies that orbit it. You know how the Earth has the moon going around it and the sun has planets going around it? Galaxies often have little galaxies orbiting them. So this is the Andromeda, and this is one of its companion galaxies or satellite galaxies. The other one is this one right here. Milky Way has two as well. If you're in Australia or South America or South Africa, you could see them in the sky. They're called the Magellanic Clouds. They look like little chunks of the Milky Way set off to one side, separate from the Milky Way itself. We can't see them from Maine, unfortunately, no matter how dark our skies are, because the Earth is always in the way. So there we have the Andromeda galaxy in the western sky. I want to come all the way back down around to the south here one more time. And if you review real quickly, we can see Orion the Hunter here. Let's bring him back up. And remember, he's fighting with Taurus the Bull right there. And we had one visitor in Taurus, and that was Mars. But there has been another visitor recently in Taurus, and it's going down towards Orion's shield right now that he's holding in his hand. And that is, we had a comet in the sky. Maybe you've heard of the Green Comet. Its real name is C/2022 E3ZTF. Pretty nice name, huh? C means it's not periodic. It doesn't come around every year. It hasn't been around. If it's been around, it's been thousands of years. So it's a comet that we've never seen before. 2022 means that's when it was discovered in 2022. And that makes sense. E3 means it was discovered in 2022 in the first 2 weeks of March. You might wonder, how do they get that? Well, the year's divided into quadrants. A is the first 2 weeks of January. B is the second 2 weeks of January. C is the first two in February, and so on. E is the first 2 weeks of of March. 3 means it's the third one that was found in that time of year in that year. So it's the third comet found in the first 2 weeks of March in 2022. Seems like a lot of explaining to do for 3 little letters, right? And ZTF stands for the telescope that found it, an automated system. If you find a comet before these automated systems do, they'll name it after you. So let's say my friend Larry, who was on here, his last name is Burrs, and he finds a comet and he calls it in before anyone else, it becomes Comet Burrs. Now, if he calls it in and then a half hour later I call it in, then it would be Comet Burrs Meter. His name goes first because he reported it first. And if Amanda calls it in third, it's Comet Meter, Burrs Meter, the Liberty. And if someone else one of the rest of you calls it in after that, they say too late. They only will add 3 names. Then you're just too late after that. But now lots of comets, and like you hear pan-stars. There's a whole bunch of comet pan-stars and comet ZTFs. Those are automated systems that are studying the sky, watching for asteroids and things, and they find these comets. And that's what this one was found. Let's see where it is tonight. If you have seen it, you know you can't really see it without a telescope or without binoculars. And it should be, there it is right there. That little dot. Didn't notice it before, did you? Well, let's go see it. It's actually not that dot. Well, yes, it is that dot. No, it's not. It's this dot right here. It's very faint, and it's getting fainter now because it's moving out away from the sun. And as it goes away from the sun, it's losing its brightness. So comets are essentially big, dirty snowballs. Imagine a snowball as being around Saddleback Mountain, and it's orbiting the sun. It's full of dirt. It's like a dirty snowbank in the springtime. It's a lot of snow and ice and dirt and stuff in there. And as it goes around the sun sublimates the snow, which means it turns it not to a liquid, but directly to a gas. And it forms a giant fog bank around the snowball. Now, the snowball might be several miles in diameter at the most, but that fog bank can be 100,000 miles in diameter. And then as the snowball and the fog bank get close to the sunlight pushes the fog bank back, and that's what creates the comet's long tail. Now, this comet, when you looked at it through binoculars, you don't see any tail. You just see a fuzzy patch of light. And I thought, just to finish up, to do a little differently, I've done some observations in the comet 8 times now, and I've taken some pictures of it. So I'd like to just change from Stellarium and show you some pictures of the comet, if you like, and explain to you what we're looking at a little bit. So I'm going to stop sharing for a second, and we will go back to screen share. And now we'll go to Lightroom. So this was a couple weeks ago. This is Lake George Park in Skowhegan, looking north. This is Lake George down here. Nice place to go swimming in the summer. And you could actually see this comet in the sky with your eyes. And it's right there, right above my little cursor there. So let's zoom in on it. That little dot right there, that's what it looked like to your eyes. Now, if you didn't know what you're looking for, you can imagine you're not going to notice that, right? I only noticed it because I knew exactly where it was supposed to be, because I'd studied Star Trek before I went out that night. And I could see it there. I was with 2 guys who had never seen a comet before, and they couldn't see that. So what we did is we looked at it with binoculars. With the binoculars, it looked like this. So you got this little patch, this little star-like thing, and it's got a little haze around it, whereas stars don't have a haze around it. So that's kind of what you expect to see in binoculars. Now, if you saw Comet Neowise a couple of years ago, in the midst of COVID, we had a brilliant comet with a great long tail, and you didn't have to use anything to see it. It was huge and bright. The tail was about 15, 20 degrees long across the sky. You could not miss. This one, you can see, if you know how to look at faint objects, you can actually get a sense of a tail going off this direction up here. And you might say, he's crazy, I don't see that. Well, you learn how to see these things if you study long enough. But if you take a longer exposure photograph, it starts to show up better. This is just slightly longer, but the tail's not showing up, but the color's starting to come through. Over time, when you expose things longer, if you expose them too long, it gets washed out again. There's a point where the color starts to come through. And now you're starting to see perhaps why the comet is called the green comet. It's got a distinct green color. That's from disodium in it, which when the sun interacts with it, it makes it glow with a green light. And it's not an uncommon thing. A lot of comets have this green color to them. So it makes it kind of pretty though to have that color. Now, if you do take a longer photograph, this exposure is 2 minutes long. It's actually about 3 2-minute exposures stacked on top of each other. And when you do that, it's like taking a 6-minute long exposure. So you start seeing the tail start showing up a whole lot better. So the snowball that's the size of saddleback or so is right down in the middle of this thing here. This is the coma, or the fog bank around it. That's 100,000 miles roughly from side to side this way. And then the sun is down in this direction because the tail always points away from the sun for the most part, because the sunlight pushes the fog bank back. When you draw the sun, when you're a kid, you draw a circle and put rays coming out. Those rays really exist. It's the solar wind, the energy flowing out of the sun, and it pushes the fog bank away. It's not strong enough to push the comet around, but it'll push the fog bank back and create this long tail dragging out behind. Now, comets actually can have 2 tails. One is the gases the coma that gets blown away. It's called the ion tail because it gets ionized by the energy in the sunlight. And then this, I said, was a dirty snowball. So if you're melting the snow, it releases the dirt and the dust, and it creates a dust tail. And they often separate out. The ion tail always points directly away from the sun, while the dust tail will sort of get left behind, and it can separate out depending on how the comet's moving. And sometimes you see what looks like an anti-tail going towards the sun, because that's the side that's melting. And when it melts, it shoots out with jets of gas shooting out of this dirty snowball right towards where the source of the heat is, the sun. It shoots out and then it gets blown back to make a long tail going off like this. Now, if you don't want to do photography, the first thing I did the first night I saw it, this was on the 18th of January, I just sketched it out. And that's a fun way to observe. In some ways, you learn a lot when you draw sketches. You start drawing out a map of some of the bright stars in the field, looking through your telescope, and make whatever you see for the comet. If you see a tail, draw the comet in and draw the comet's tail in. Or in this night, all I saw was a fuzzy patch. And so that's what I drew in there. And then I drew some labels to label the names of some of the stars so people know exactly where I was looking. Now, some nights you go out, this is at Lake George too, and you can see the comet is right there. We got there and the clouds moved in on this night, and you couldn't see the comet at all at first. So we just turned around and the sky was still beautiful to the south. So that's our Orion Nebula we saw earlier. So here's the Orion Nebula right here, that birthplace of stars. Another little nebula up here called the Running Man Nebula, which is one of my friend Larry's favorite nebulas up here. Same thing, big cloud of hydrogen gas. There are the Pleiades, the 7 sisters, those teenage stars we talked about. Here's another group, which I didn't show you. It's in Cancer the Crab, which is between the Gemini twins and Leo. Very dark constellation, doesn't show up very well. But another little open cluster known as the Beehive Cluster. And I'll leave you with this. This is, if you look carefully, you can see Orion right here. See Orion's belt? There's Rigel and Safe. Here's Betelgeuse up here and Bellatrix. A lot of stars here, though. This is a long exposure, which gets fainter. You gather light over time, so the faint stars start showing up better. But the interesting thing, you see how colorful all these stars are. Those are the actual colors of the stars. Now, for the most part, stars look white to us, unless it's a bright star like Betelgeuse, where you can see that red star, or Aldebaran, the eye of Taurus the Bull, you can kind of see it's orange. Sometimes when you look at Rigel, you can see a little bit of blue color. Well, the bright stars will start to show their colors because they're bright enough to affect the cones in our eyes, which need a lot of light to work. Most stars just look white. It doesn't mean they're white. It's just our eyes can't see faint color. Well, when you take a photograph of all the stars, and if you're making a nice sharp focus, they still pretty much look white, other than maybe the really bright ones. The interesting trick is to turn it just slightly out of focus. This is totally just a little out of focus. It makes the images a little bit broader. And then you take the picture, and when it first came back, there's a little bit of color there. But if you bring up the saturation in your photo program, like Photoshop, and what that does is it takes the colors that are hidden there and brings them out. And it shows you the true colors of the stars. This is what the sky would look like if we had eyes that could see the colors from the stars. The night sky would be filled with colorful stars. There are white stars, but there are no more white ones than blue ones, or red ones, or orange ones, or yellow ones. Stars come in all different colors. Our eyes just aren't good enough to see those faint colors. So just think about that the next time you're out there staring at the stars. All right. Well, I hope you've enjoyed this tour tonight. It's been fun sharing all this with you. And I hope you get outside and get a clear night some night soon and look at the stars. And maybe in March, we'll get a clear night and I'll get to come to Rangeley. I love that when I get to come up and go out in the sky and show you these things in the real sky. And hopefully we'll get to do that in another month. Sooner or later, we got to hit it right, Amanda.
One of these days.
One of these days.
Just to reiterate what John said, thank you again to everybody for joining us this evening. Thank you again, John.
You're welcome.
Save the date for March 16th. That's our next dark sky tour. And fingers crossed we'll be in person at the Rangeley Lakes Trail Center. And visit rlht.org for future programs like this and to learn more about the Rangeley Lakes Heritage Trust and the other things that we do. I hope everyone has a great evening. Good night.
Thanks for coming, folks. Thanks, Amanda.
Thanks, John.
You're welcome. Take care.